Imagine standing in the middle of a desert and seeing solar panels stretching farther than you can see. Millions of panels covering an area that looks more like a city than a power plant. But the most impressive part isn't the number of panels. It's what happens behind them. Thousands of megawatts of electricity must be collected, converted, controlled, and transmitted across enormous distances. China didn't simply build a giant solar farm. It built an entire energy system in the desert. Being developed in regions with huge amounts of sunlight and vast amounts of available land. That creates the perfect conditions for large-scale solar generation. But producing electricity is only the first step. Engineers also have to move that electricity from remote deserts to the cities that need it. And that's where this project becomes much bigger than a solar farm. The desert seems like an unlikely place to build a massive power system. There are few cities, few roads, and almost no traditional infrastructure. But for solar engineers, the same emptiness becomes an advantage. Large solar installations need enormous amounts of land. In densely populated regions, finding enough continuous space can be difficult. In China's northern and western regions, huge areas of relatively open land are available, and these areas can receive intense sunlight for long periods of the year. That means engineers can install solar panels across enormous surfaces without competing directly with dense urban development. But there is another advantage. The solar panels don't need to be placed randomly. Engineers can carefully arrange rows to optimize sunlight exposure while leaving enough space for maintenance, electrical equipment, and access roads. Thousands of individual panels are connected into larger electrical units. Those units feed electricity toward inverters, which convert the electricity into a form suitable for the grid. Then transformers increase the voltage for long-distance transmission. So what looks like millions of separate panels is actually one enormous coordinated electrical system. But building the panels is only half the challenge. The desert creates serious problems of its own. Dust can accumulate on panels and reduce their performance. Strong winds can carry sand across the site. Extreme temperatures can affect equipment. And maintenance crews may have to travel across enormous distances just to reach individual sections. That means engineers have to design the entire power base around the environment. The desert provides the sunlight, but it also tests every piece of equipment. And once the electricity is generated, the biggest question begins. How do you move gigawatts of power from the middle of nowhere to the cities hundreds or thousands of kilometers away? A giant solar base isn't one enormous panel. It's a massive collection of smaller electrical systems working together. Each solar module converts sunlight into electricity. Groups of modules are connected into strings. Those strings feed larger electrical units. Inverters then convert the electricity into grid-compatible alternating current. From there, transformers increase the voltage. This is essential because moving electricity over long distances at higher voltage reduces transmission losses. But controlling such a massive power plant is a major engineering challenge. Clouds can suddenly reduce solar output. Dust can lower panel efficiency. Temperature changes can affect equipment. And the amount of electricity produced changes continuously as the position of the sun changes. So operators need monitoring systems that can track power generation across the entire site. Sensors and control equipment provide information about individual sections. If one area develops a problem, engineers can identify it without inspecting the entire facility manually. This creates something very different from a traditional power station. There may be no giant boiler, no massive turbine hall, no single machine generating all the electricity. Instead, the power comes from thousands or millions of small photovoltaic cells operating together. But there's a problem with that system. Solar power disappears every evening, and electricity demand doesn't. Factories keep operating. Homes still need electricity. Cities still need transportation and lighting. So engineers need another piece of infrastructure to make this enormous solar base useful. A way to store, balance, and move the electricity when the sun isn't available. And that's where the desert power base becomes connected to something much bigger, China's national power grid. Generating electricity in the desert is only useful if you can deliver it to people. And China's biggest solar bases are often located far from the country's major population centers. That creates a massive transmission challenge. Engineers use high-voltage transmission networks to move electricity across enormous distances. The principle is simple. Increase the voltage, transmit the electricity, then reduce the voltage again near the areas where it will be consumed. Higher transmission voltages allow large amounts of electrical power to travel long distances with lower losses. But the infrastructure required is enormous. Power from thousands of solar installations must first be collected and combined. Transformers then raise the voltage before the electricity enters long-distance transmission lines. At the other end, substations reduce the voltage and distribute the electricity into regional networks. This means the solar base isn't really a single power plant. It's the starting point of a huge electrical pipeline. And unlike a traditional power station, solar generation constantly changes. Output rises in the morning, reaches its peak around the strongest sunlight, then falls toward evening. So grid operators have to continuously balance generation with demand. If solar production suddenly increases, other generators may need to reduce their output. If clouds reduce solar production, other sources or storage systems may need to compensate. That makes forecasting extremely important. Engineers use weather data, solar radiation measurements, and real-time power monitoring to predict how much electricity the solar base will produce. The better the prediction, the easier it becomes to keep the grid stable. But even with efficient transmission and accurate forecasting, one major problem remains. What happens to all that solar electricity after sunset? Solar power has one unavoidable limitation. The sun isn't available all the time. During the day, a giant solar base can produce enormous amounts of electricity. But after sunset, photovoltaic panels stop generating power. This creates a mismatch between electricity production and electricity demand. One solution is energy storage. Large-scale battery systems can absorb electricity when solar production is high and release it later when generation falls. But storing electricity at the scale of a giant power base is a major engineering challenge. The batteries need enormous capacity. They also require thermal management, monitoring systems, fire protection, and sophisticated control equipment. Another approach is pumped storage hydropower. When electricity is abundant, water can be pumped to a higher reservoir. Later, that stored water flows downhill through turbines and generates electricity. This effectively converts surplus electrical energy into stored gravitational energy. China has also been developing hybrid renewable energy bases that combine solar with wind and other generation sources. The advantage is diversification. When solar output falls, another source may still be producing electricity. But storage and hybrid generation don't solve everything. The grid still has to transport the power. And the further electricity travels, the more important transmission efficiency becomes. That's why China's desert renewable energy strategy combines several technologies at once. Solar panels generate the power. Storage helps balance it. High-voltage lines transport it. And grid control systems coordinate everything. The solar panels may be the most visible part, but the real engineering achievement is the invisible system connecting them to millions of consumers. And building that system across the desert creates one final challenge. How do you keep millions of panels operating efficiently in one of the harshest environments on Earth? A solar panel doesn't need much maintenance, but a solar power base containing millions of panels is a completely different engineering problem. The desert constantly attacks the equipment. Dust can settle on the photovoltaic surfaces and reduce the amount of sunlight reaching the cells. Strong winds can carry sand across the site. Extreme temperatures can affect electrical components. And because these installations cover enormous areas, even a small reduction in efficiency can become significant when multiplied across millions of panels. Engineers therefore design maintenance systems specifically for the environment. Panel surfaces can be cleaned using specialized equipment and carefully managed water resources. The challenge is finding the right balance. Cleaning improves power generation, but using too much water defeats the purpose of building renewable infrastructure in an arid region. So engineers increasingly look at automated cleaning methods, optimized schedules, and systems designed to reduce water consumption. Monitoring is equally important. Sensors and electrical controls can identify abnormal performance in individual sections. If one group of panels produces less electricity than expected, operators can investigate the problem without manually checking the entire solar field. This is especially important because these facilities can stretch across enormous distances. Maintenance isn't simply about fixing broken equipment. It's about keeping the entire system operating close to its designed efficiency. The panels, inverters, transformers, transmission equipment, and control systems all have to work together. And there is one final challenge that engineers cannot eliminate. The sun itself is constantly changing. Clouds move, temperatures change, and every evening, solar generation falls to zero. So the system must constantly adjust. The biggest solar farm isn't really a field of panels. The most important part of China's massive solar bases isn't the panels. It's the infrastructure connecting them. A modern renewable energy base combines generation, storage, transmission, monitoring, and grid control into one coordinated system. Solar panels generate electricity during daylight. Storage systems can help shift some of that energy toward periods of higher demand. High-voltage transmission lines move electricity from remote regions toward major population centers, and control centers constantly balance supply and demand. This changes the traditional idea of a power station. Instead of one giant machine producing electricity, you have millions of smaller machines working together. Each panel produces only a small amount, but when millions operate simultaneously, their combined output becomes enormous. The engineering challenge is therefore one of scale. A problem affecting one panel may be insignificant. A similar problem affecting hundreds of thousands can become a major loss of generation. That is why automation, monitoring, predictive maintenance, and centralized control becomes so important. And the same principle applies to the grid. Solar generation can rise rapidly during strong sunlight and fall as clouds or evening arrive. The grid must respond continuously. That requires accurate forecasting and coordination with storage and other power sources. So China's desert solar bases represent more than a massive collection of photovoltaic panels. They are a new kind of infrastructure system, one designed around renewable generation at enormous scale. The desert provides the space. The sun provides the energy. But engineering connects those two natural resources to the people who actually need the electricity. And that is what makes the project remarkable. China didn't just build a giant solar farm. It built a giant machine for turning sunlight into national-scale electricity. From the ground, it looks like an endless sea of solar panels. But underneath that surface is a much more complicated story. Electricity is generated, collected, converted, stored, controlled, and transmitted across enormous distances. Every panel is a small part of a system containing millions of components. And every component has to work together. That's the real engineering achievement. Not simply covering a desert with solar panels, but turning an environment with almost nothing into a massive source of electricity. The desert provides the sunlight. Engineering provides the infrastructure. And the grid turns that sunlight into something useful for millions of people. The future of energy may not be built around one giant machine. It may be built from millions of small machines, working together at a scale we've never seen before.